Okay, so now we get to the yummy part of circuits. Now, I know it sounds crazy, but this is like the easiest sums in question paper 1 if you write 2 question papers. If you do it in a structured way, and if you have a little bit of understanding about what's going on with the electrons and the teams, the current, then it makes a lot of sense. And if you use my method, you will always get the right answers for one thing, and you will know that you're right. And that, in my book, almost counts more than just getting it right. Okay, this example that I'm using comes from the Siyavula textbook. I will put the link below this video if you want to access the other examples and questions as well. So what we are going to do is 2 things. Now, this is a very pretty circuit, but it doesn't look exactly the way that we've been drawing it. So I'm going to show you another way of drawing it. And then we're going to answer the questions, but you will see the questions aren't on the screen yet. And that's on purpose. Okay, I don't want the questions to start freaking us out before we've had a chance to figure out what we actually know. Okay, so the first thing that we're going to do is we're going to redraw this circuit. And the way we are going to do it is we are going to cut it off there. So this is a circuit, it's a wire, right? So we're going to cut the wire there, and then we are going to fold this part of the circuit to the left, and we are going to take this part of the circuit and fold it to the other side. My video on the screen is flipped, so now I have to flip left and right, and I cannot remember which is left or right, even on my own body. So this is difficult. So I'm going to redraw it on the next screen, and then you can tell me if you agree. Okay, so this is our circuit that I've redrawn. Okay, now the reason why I draw it like this is to make space for all the information that we're going to have to write down for doing the sums. Okay, so what I did is, this is the 4 ohm resistor, is that one there. Okay, that one didn't really move. Then on the right hand side, I just flipped it open and made a straight line instead of a angle over there, and that's fine, you can do that. And then we continue all the way down, 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 and then eventually we will get to the battery. So what I did is, with this part of the circuit, I just made the connective wire just really, really long, and you're allowed to do that. Then we have the battery. You will see that I didn't do the switch. The switch will be there, but the switch is not important for the sum, so I just left that out. And then we are back at the 4 ohm. Okay, so let's do it one more time. Let's start with the battery. So there's the battery, there's the battery. Then there's a connective wire. The next resistor that we meet is the 4 ohm one. That's that one. Okay. And then back to the one that they gave us. The next resistor that we find is the parallel circuit. And they are those. And I drew them the way I've been drawing them in the previous videos. It just makes more sense to me. And then if we keep going, we get back to the battery. And again, if we keep going back, we get back to the battery. All right. So this circuit in black, I don't know what happened to that part, it will come back now. The circuit in black is exactly the same circuit. I just changed the orientation maybe. Okay, now the other thing that we need is we need to put the information onto our paper. And to do that, I'm going to write it below the resistors. And before I do that, I need to give them names. Okay, so we're going to call this resistor 1, resistor R1. This one we will call resistor 2A, and this one we will call resistor 2B. All right. So if we look at resistor 1, we know the resistance is 4 ohm. Okay, they give it to us there. And then the voltage is there as well. So the voltage of 1 is 6 volts. All right. And then if we look at R2A and R2B, I'm just going to give them names there. We know the resistance of R2A is 8 ohm, and the resistance of R2B is 5 ohm, and it doesn't seem like we have any other information on the circuit itself. Let's just go back. So when switch S is closed, the potential difference across the 4 ohm resistor is 6 volts. Any resistance from the battery and connecting copper wires can be ignored. And we know that is true because we know that fairies don't use fairy dust between obstacles. Okay, now remember, we've done this often enough now that you know the first time that you are met with new information, it is scary. It feels like you don't know what's going on. It is going to be okay. So let's struggle through this one. Let's feel like we don't know what's going on. And then with the next one we do, it'll be easier. Let's just go back to our fairies for a second. Okay, our little electrons. So if the electron leaves the battery over there, it is going to use some energy there, and it will use some energy going through resistor number 2, whichever path it takes. Okay, and we know from previous videos that whatever happens to the energy is the same that happens to the voltage. So if we look at the series circuit, meaning the main circuit, we know that the total energy will be split up between obstacle number 1 and obstacle number 2. Okay, now obstacle number 2, I'm going to call it WP. Okay, that is for the parallel circuit. And whatever happens to the energy also happens to the voltage. So the total voltage will be split up between the first resistor and the parallel portion of our circuit. Okay, now there are 2 more equations that I need here. The one is for my team. Okay, so what happens to the team? So we used 5 fairies in the previous video. So if 5 fairies leave the battery, all 5 will go through resistor number 1, and all 5 fairies will eventually go through resistor number 2, the parallel part. So does it make sense that my total current will be the current going through 1, and that will be the current going through the parallel path? Does that make sense? So the energy gets split up, the voltage gets split up, but the current remains the same throughout. Okay. And then the last thing that we haven't really worked on yet, I'm going to take my frame away, is a formula for the total resistance. And this one is easy, you just add them up. So it will be the resistance of number 1 plus the resistance of the parallel path. Okay, so the total resistance, and we'll get to that next. So if you look at the main circuit, then these are the formulas that we are going to use. And in truth, this first one we're never going to use. It's very rarely asked, but maybe I'll put it in the exam just because we've been working with it. Okay, now we can look at the parallel path. It's just this little path here. So just this path. It has its own set of equations. And you know them. You know them in terms of fairy dust, and you know them in terms of fairies. So let's just write them in sciencey speak. So what happened to the energy? So the energy that our little electron had there, did the energy split up, or did the energy remain the same? So when Tinkerbell was there, she had a certain amount of energy left. And throughout all the previous videos that you've watched, we saw that she would use the same amount of energy whether she went through the first leg or the second leg. So does it make sense that the energy of the parallel path in total will be the same as going through 2A, and it will be the same as going through 2B? And whatever happens with the energy happens with the voltage. So the voltage across the parallel part of our circuit will be the same as over 2A, and it will be the same as over 2B. Okay. If we look at the teams, if we look at the current, what happened to the current? So we had 5 fairies coming out of the battery, 5 going through resistor number 1. But when they got to this junction, some of them chose the top one and some of them chose the bottom one. So the current going through the parallel path or piece of our circuit will be split up. Some will go through 2A and some will go through 2B. And then for our resistance, there's a funny little formula that you might know. It's 1 over R2A plus 1 over R2B. Okay. So in this video, you have learned a couple of things, of which 2 is important. The first one is how to redraw your circuit. The next one is sort of obvious, just to make your information lists. I would like to see a little bit more space, but you work on paper, not on a screen. And then the second one is the formulas that we're going to be using. And if you've done this, then the rest of whatever question they throw at you, you will be able to do. So if you do the preparation work, okay, if you do the work that's on the screen now, you will be able to do any electric circuit sum that they give you. Okay, so I'm not going to answer these questions yet. I want us to redraw and make the list of the information for one more. Okay, so this electric circuit comes from an old exam paper, 2018. It's the National Senior Certificate. It's freely available on the internet. And again, I didn't even copy and paste the questions because right now the questions aren't important. And I would really strongly advise you that when you get your own exam paper, is don't look at the questions. First, do your preparation, because by the time you get to the exam, you will know how to do this preparation. It'll be second nature. You won't have to think. And because you don't have to think, your nervous system can relax a little bit, and that helps with stress regulation. Okay, so if we just look at this, it looks very Demarcade, I know. So the first thing that you can do in your mind, I can't do this on the screen, although maybe I can, let's see, is this voltmeter reader I'm going to take out because it's not important for our sums. Okay, the value is, but the physical structure thing is not. The other thing that you can ignore is the current meter, the ammeter, and this is another voltmeter that we're going to take out. There's another ammeter that we're going to take out, and another one. So when I redraw my electric circuit, I am only worried about the battery, the connective wire, and the resistors. That's all. I don't want any funny meters in there because it messes things up. Okay. What I'm going to do with this one, I'm going to redraw it here at the bottom. Or actually, I'm just going to redraw it here. So this is our resistor. I'm going to change it into a block because we've been using blocks. Okay, so there's our parallel path. And then here we have another one. And then if I continue with this connective wire, eventually I'll get to my battery. And again, I don't worry about the direction of my battery because for the sums it's not important. And then if we look at the other side, if I just continue, I know we have a switch, but the switch is not important for the sums. And then I get back to my battery. So if you want, you can redraw the circuit like this. Okay. But I don't. I just want this straight line. So what I do is I take all the elements of my electric circuit and I fold it open so that all the elements are in a straight line. It makes it nice and neat, and it helps to order the information that we're going to add now. I'm going to erase that, and I'm going to take this and just move it up, and I'm going to take that away. Okay, now we need names again, just like previously. So we're going to call this one R1, R2A, and R2B. If we look at this whole parallel piece together, we're going to call it RP for parallel. Okay, so here we have a battery. This battery will have a voltage, it will have a current, and it will have a total resistance. So the resistance is not the resistance of the battery, it's the total resistance of the current, but we'll get there. If we look at R1, we will have a voltage, we will have a current, and we will have a resistance. Okay, and then for the parallel part, we're going to have 3 information lists. We will have one for the whole section together. So we will have a voltage for the parallel path in total. We will have the current, and we will have a total resistance. And then that we will break up into VIR for 2A, 2A, and 2A. And then we have a VIR for 2B, 2B, and 2B. Okay, can you see how we are ordering the information? I know we don't have any values yet, but that is okay. All right, let's go back to our little electron and just see what happens. So if we look at the current, all the fairies going through, we know that the current, the team coming out of the battery, will be the same as the current going through R1, and it will be the same for the current going through the parallel piece. Okay, so now you can take your highlighter, let's make it yellow, and we are going to draw a straight line through, all the currents, meaning all the currents are the same, because we know with these little formulas that we wrote, that we're going to write now again, the current is the same in the main or in the series part of the circuit. And if we go back to the energy or the voltage, we know that the energy used for leg 1 and the energy used for leg 2 will be the same. So I'm going to take another color and I'm going to highlight those two. So visually, I'm showing myself that if I have any one of my I values, I will have all of them. And if I have either the one or the other V value here, the voltage, then I will have the other one, and that will equal the voltage of the parallel section in total. Now, if I had this paper in front of me, I would make these next to lists of formulas, I would make it underneath. So if you're following with me and you're making notes, which I hope you are, just do it underneath. I don't have enough space, so I'm going to do it here on the right hand side. So if we look at the series circuit, meaning the main circuit, and the main circuit, if you want to see it, I'm going to make it yellow. It would be the straight line going through. Okay, so we know the energy coming out of the battery will be split up between the obstacles. So V1 plus Vp. Okay, and that is the same as the voltages. So the total voltage will split up between resistor number 1 and the total resistor number 2, irrespective of where we're going. The current will be the same everywhere. So the ferries coming out of the battery will be the same as the ferries going through resistor 1, and it will be the same for the ferries coming out of resistor number 2, which we call P. Okay, and then for R, it's just the same as for V. So RT equals R1 plus RP. Okay, and then this I'm going to make yellow again. Okay, so visually I can see all these pieces of information are coming together. And then the last one we have is the parallel one. So now we're just worried about what's happening there. So we know the energy is the same. So the energy just before the junction will be the same as the energy used in leg 2A, and it will be the same as the energy used in leg 2B. And then whatever happens with the energy happens with the voltages. So V to A, and that equals V to B. Okay, and I'm going to make that blue. Okay. And then we know the current, the team, needs to split up. So that will be I to A plus I to B. And then for my last formula that I need to squash in somewhere is to determine the resistance of the parallel piece, and it looks like this. Okay, when we start using it in the sums in the next video, you will be fine. Okay, so this is all the information we need. This is the hard work of circuits. So if you can do everything that is on the screen now and you understand it, then you will be absolutely fine with the sums that come next. Okay, let's do 2 more. So this one again, it's from an old departmental question paper. So if we just look at the elements in the circuit, we have the battery over there. It has a voltmeter. I'm going to take that out because it's not important for our sums. Okay. Then we have a switch. The switch again isn't important. And then we have our first resistor. It's this 4 ohm one. It has a voltmeter reader, but I'm going to take that out. And then if we continue, we have this parallel junction again, and it has a voltmeter. So I'm going to take that out as well. So I'm not worried about the numbers yet. I just want to draw our little picture. What I'm going to do now is, because these resistors of mine are already in a straight line, I'm just going to redraw them. So let's start with the 4 ohm one. And then we have the parallel one. Okay, now we still need the battery. I prefer to put the battery on the left. It just makes sense with the sums that come up later. So this is our circuit. So if the names aren't given, you need to add names. In the exam, they will have proper names so that we all know which ones we're talking about. I'm going to call this one R1A and R1B. And this one is R2. And this parallel portion is also, if we look at it in total, it is RP. Because remember, when we did the ferries, we had this picture where I had a question mark and you couldn't see what was at the bottom. So it is very possible, and you can do that, is to take the parallel portion and just swap it with one resistor. And if that would happen, we would just call it RP. Okay, now we need our information list. We know it's VIR for everyone. There's a VIR, VIR. And then for the parallel portion, we have a VIR for the total values, and then we split them up in VIR again. So the battery ones will be totals, T's. This one will be parallel. This one will be 2, 2, and 2. And then this one will be 1A, 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 and 1B, 1B, 1B. Do you see how fast it is to put the framework for your preparation in? Okay, now we need to go back and we need the physical values. And in this case, everything is contained in my picture. It's always a good idea just to read the words that accompany the picture. So if we look at the battery, we don't have any information. Okay, now I know this is a V1 and we decided to call it a VT. It is not a problem. Okay, so don't worry about the subscripts now. We have these two resistors in parallel. The one is a 2 ohm and the other one is a 6 ohm. And if I look at my picture, it means that R1A will be 2 ohm and R1B will be 6 ohm. And then we have this 4 volt, and that 4 volt, you'll see this voltmeter is across the whole parallel piece. Now it would have been better if I drew it like this so that you can see it properly, but that 4V needs to come up here. Okay, and then with this last one we have a 4 ohm and we don't know what the voltage is. Okay, so this is our preparation. The last thing that we need to do is we need to write these formulas, and that is easy because we remember what happens to the energy and we know what happens to the team. So if we remember the team, the number of fairies coming out of the pixie dust tree will be the same as the amount going through obstacle number 1, so coming in and going out, and it will be the same as the number of fairies going through obstacle number 2. We're going to write that down now. And in terms of energy, the energy that we use for the parallel piece will be the same irrespective of which one of the legs we use. So let's work with the main part of the circuit, the series part. We know something about the energy. So the energy that electrons or the fairies get at the battery will be split up between the obstacles. And in this case, we have 2 main obstacles. We have the first one and the second one. And whatever happens to the energy will happen to the voltage as well. So the voltage will split up. The current, the team, will stay the same throughout. And the resistance we just add together. So the parallel resistance plus R2. And then if we look at the parallel piece of our circuit, then we know the energy will be the same. The energy usage will be the same whether we go through leg 1A or whether we go through leg 1B. And whatever happens to the energy happens to the voltage as well. So the voltage of the total parallel piece of our circuit will be the same as leg 1 and the same as leg 2. Okay. And then we also know that the team needs to split up. And to determine the resistance, we use this funny formula. And then we're going to use our color just to make it easier for ourselves to find the different numbers. Okay, and this is the preparation for the third one. Okay, so this is our last one. Again, it comes from a past paper. I've modified it slightly because I think we are tired of the 3 that we've done thus far because they're all the same. Okay, so if we look at the elements again, pretending that we are a little fairy, we start at the fairy dust tree. There's a voltmeter, it's not important. Then we have our first little obstacle. It has a voltmeter again, that's not important, so we're just going to take that out. So especially these lines are the ones that confuse you. So just take it out. All right, so we go through the first obstacle down, and now we have a junction. And in this junction, this A2, which is usually a circle, is your ammeter. It measures the current. So we're just going to take that out. Again, it's not important. And this little round one we're also going to take out. Okay, so we went through the 4 ohm resistor. Then we got to a junction. Then we can either go through the 6 ohm or through the 3 ohm. We get out the other side, and then we pass through a last one. And you are welcome to use Tipp-Ex in the exam if they bother you. But with enough practice, you will be able to sort of just ignore the circles because they are not important. Now we're going to redraw our circuit. I'm going to start with a parallel piece. On the right hand side we have another one, and on the left hand side we have another one, and then on the far left hand side I'm drawing my battery. Again, the orientation of the battery is not important for the sums. Okay, we are going to give them names. So this is resistor 1. This total piece will be resistor 2. So this one will be R2A and R2B, and this will be resistor 3. So we're just going to add the names. So this is R1, this is R2A, this is R2B, and this is R3. Next, we're going to do our information list. So it's VIR for all of them. So the battery is all the totals. This one is 1, 1, 1. These totals will be just for the parallel piece, and this one will be for 3. And then the parallel piece we split up into 2A. Yeah, easy. Okay, then the last thing that we need to do is we need to write our little formulas, and they all work exactly the same as the previous 3 examples. Our current in the series circuit, the main circuit, will all be the same. The teams going in and out will be the same. And when we look at the voltages, it's the same as the energy. So the energy going through leg 1 will be the same as the energy going through leg 2, and that would be the same as the energy going or being used throughout the parallel piece. So you can maybe pause the video and write it yourself, and then unpause it to see if you agree with me. Okay, so if we start with the energy again, the pixie dust that Tinkerbell gets, she needs to use throughout the obstacle course, and she divides that between the obstacles. And we have 3 main obstacles. And whatever happens with the energy happens to the voltages. And if we look at the teams, we know the team needs to move through all the obstacles as a unit. And here follows the equations for the parallel piece.